In the last lecture, we distinguished between metals, insulators and semiconductors on the basis of their conductivity. We found that the number of free electrons in metals is very high, and therefore, these high density electron gas becomes degenerate, because one of the conditions for the gas to become degenerate is very high density. So, the conditions are there for the gas to become degenerate. What does this mean? This means that a degenerate gas occupies all the energy states below Fermi energy, and above Fermi energy there are very few states which are occupied. And this distribution which is obeyed by the degenerate gas is called Fermi Dirac distribution. And as you can see, at 0 degrees Kelvin, all energy states are occupied below E f and none above it. That means, the gas is completely degenerate. Now, we shall see how bands are formed and how on the basis of these bands we can again distinguish between conductors, semiconductors and insulators. How do the bands originate? Remember that the number of electrons, number of atoms in a gas, and therefore, the number of electrons in the outer shells, this number is very, very large. And there is this crushing of the outer shells because of the very close packing of the atoms. What happens then is that the shells, individual shells lose their character and they are transformed into continuous bands. What does it mean? That means, in a band there is a continuous variation of energy. Remember, in a shell the energy is fixed and various shells have discrete energies, as you learned in atomic physics. Here a band has a large number of there is an energy distribution of energies in a band. We shall take the example of metals, sodium in particular. Just as in atoms you have 1 s state, 2 s states, 2 p state, 3 s state and so on, those shells. In a solid where there is a large number of atoms present and they crush each other, the bands are formed, and these bands also are 1 s, 2 s, 3 s and 2 p, like just like this 1 s, 2 s, 2 p, 3 s, these becomes bands. Let us see the bands in sodium. In sodium, you know, 1 s has 2 electrons, 2 s has 2 electrons, 2 p has 6 electrons and 3 s has 1 electron. That is the atomic structure or the electronic structure of the sodium atom. When sodium atoms are packed together in a piece, then there is a crushing of individual atoms, then these shells they become bands. This is 1 s band, 2 s band, 2 p band and 3 s band, and 3 s band has only 1 electron. All these are full, 2 again and 6 and all these are full, but this one 3 s band has only 1 electron in the shell, but here there is a continuous distribution of energy and 3 s is partially filled. So, within a band an electron can take continuous range of energy values, not one fixed value, but a continuous range of energy values. The 3 p band is completely empty, 3 p is completely empty in the sodium. Since electrons can take a range of continuous energy values, the filled and unfilled 3 s band overlap. You see, since in this 3 s electrons can take continuous range of energies, these two overlap, the unoccupied and the occupied one, as far as energy states are concerned. This overlap is true of metals in general. As we saw, bands may be filled, empty, partially or partially filled. Again this example of sodium, filled, partially empty and so on. The highest energy filled band defines the valence band. So, all these colored are the valence bands, and the unfilled, this one unfilled band is called the conduction band. So, we have conduction band and we have valence bands. In this band, electrons are free to move. In the conduction band, the electrons are free to move, and therefore, they can conduct, they can respond to the external electric potential. They contribute to conduction of electricity. So, these conduction band electrons, they contribute to the conduction of electricity. In addition to filled bands and partially filled bands, there are bands which are forbidden. That means, no electron can exist in these bands, which no electron can occupy by the rules of quantum mechanics. The width of these bands determines the conduction properties of solids. So, this is the energy gap or the forbidden bands. This is conduction bands, this is valence band, and these are filled bands. So, this one is forbidden, no electron can exist in this energy gap or in this band. Since electrons have the tendency to migrate towards lower energy states, all particles have tendency to have the lowest potential energy. The valence band is fully or nearly fully filled. So, valence band is completely or almost completely filled. We have seen that at absolute 0, all energy states up to Fermi energy are fully occupied, and no state above Fermi energy is occupied. Let me remind you, all states up to this Fermi momentum are occupied, and beyond that only a very few states are occupied. Therefore, Fermi level is somewhere in this energy gap, somewhere in the forbidden band, because there are no energy states above this which are occupied at 0 degrees Kelvin, and below this all energy states are full. So, Fermi level lies in between these two bands. Again the same thing, that at T equal to 0, absolute temperature being 0, all states here are fully occupied and none above the Fermi energy. Now, on the basis of bands, we shall now distinguish between insulators, semiconductors and conductors. We have already distinguished them on the basis of their conductivity. Let me remind you, metals have conductivities varying between 10 to the power 2 to 10 to the power 8 units, and semiconductors between 10 to the power 5 and 10 to the power minus 6 units, and insulators have conductivities between 10 to the power minus 11 to 10 to the power minus 19 Siemens meter inverse meter minus 1. So, this is a distinction between metals, semiconductors and insulators on the basis of their conductivity. Now, we shall distinguish them on the basis of their band structure. If this forbidden region or the energy gap is of the order of 5 to 8 electron volts, then highly unlikely for an electron to jump from here to here and cause conduction. Such substances are called insulators, because there is no possibility or very little possibility for the electrons jumping from here to here, because this gap is very large, 5 to 8 electron volts. So, if the gap, energy gap is very large, then the substance is an insulator. If this gap is of the order of 1 electron volt, so that there is finite possibility of the electrons jumping from valence to the conduction band given certain conditions, then this is called a semiconductor. So, that it is not too difficult for an electron to make a transition from the valence band to the conduction band. This kind of solid is known as a semiconductor. So, you can see that this gap is of the order of 1 eV in semiconductors. Recall the experimental observation that only a small increase in the temperature of a semiconductor increases its conductivity substantially. This you must have learned or might have done experiment in the lab, that if you heat a solid which is semiconductor by a small amount, then it becomes a good its conductivity improves a great deal. Note, however, that the small increase in temperature cannot give sufficient thermal energy to electrons to enable them to jump over the energy gap. Energy gap is of the order of 1 eV. For 1 eV, thermal energy that the electron gains, the temperature required is very high. We do not heat solids to those high temperatures. Therefore, thermal energy cannot push many electrons from valence band to the conduction band. The substantial improvement in conduction, therefore, is due to the fact that energy states above the Fermi energy, they are now available, they can be occupied because the temperature is non-zero. So, the reason that a small increase in temperature is able to send the electrons from the valence band to the conduction band in a semiconductor is that there are three reasons. The band gap is small, of the order of 1 eV. The Fermi level is in the middle of the energy gap, and the new states made available are all of energy above EF, and many of them are in the conduction band. Let me repeat this. This is of the order of 1 eV, therefore, there is a finite possibility for the electrons to jump. Fermi level is in the middle of the energy gap. All states below this are occupied at T equal to 0, but at T non-zero, energy states above EF also become available, and some of them lie in the conduction band. Therefore, as we heat a solid, a large number of electrons can go from valence band to the conduction band and improve conductivity. Now, if the valence and conduction bands overlap as they do in sodium, remember sodium, their conduction band and the valence band, they were overlapping in the state 3s. Let me go back here. You can see that in the state 3s, valence band and conduction band, they overlap, because the electrons can have a continuous range of energies. So, therefore, they overlap. So, in metals, these conduction band and valence bands, they overlap, and that means that there is a possibility, not only possibility, that in fact, the probability is very high that electrons will jump from valence band to conduction band. There is the two-way process. The electrons can jump from the valence band to the conduction band because of continuous distribution of energies. So, in a metal or in a good conductor, the conduction band and the valence band, they overlap, and this overlap makes it possible for electrons to go from one to the other. Such a solid is said to be a good conductor. Now, an intrinsic semiconductor is a pure semiconductor, the one in which impurities make little contribution to the electrical conductivity. You see, normally it is difficult to find a pure substance, but suppose we have pure substance, pure silicon for example. If it has no impurities, then its conductivity is very low. Silicon is found in abundance in nature and therefore, finds very wide use in electronic industry, but its electrical conductivity is very low, pure silicon. In the periodic table, silicon is here. On this side, there is this metal aluminum. On this side, it is non-metal phosphorus. So, therefore, this is called a metalloid or a semi-metal silicon. You can see aluminum on this side, phosphorus on that side in the periodic table, and its electronic structure is such that it has 4 electrons in the outermost shell. Its atomic number is 14 and it has 4 electrons in the outermost shell. This is when silicon has no impurities. When it has no impurities, then there is no possibility of the electrons conducting. All these electrons are bound to the other electrons of other atoms. They are bound by covalent bonds, which are very strong bonds, and they do not allow any electron to move freely. And because of these covalent bonds, there is almost no free electron, and therefore, in a pure silicon solid, there is no possibility of electrical conduction. See here, this is silicon, and it has, because of covalent band, all these electrons must have 8 electrons in the outermost shell here, and these are bound. These are covalent bonds, here also they are bound. There is no electron which is free. The covalent bonds are very strong bonds, and no electron is free, and therefore, you cannot have conduction, because unless electrons are free, they will not respond, they will not go in the direction of the electric field, or say if this is positive, then they will not go in this direction, because they are bound by covalent bonds. So, pure silicon is almost an insulator. However, Fermi-Dirac distribution does allow a few state above the Fermi energy at temperature above absolute 0. Remember the curve, that above absolute 0 there are a very few states which are occupied, and those electrons can move. So, a few electrons can move to the conduction band, leaving behind an equal number of empty spaces called holes. See, if any one of these electrons moves, then it leaves a gap. This gap is called a hole. When other electrons move into these holes, the holes shift to the location held by the electrons. I will show you here. An electron was here, electron moved to this place and a hole was created here. This electron moved to this place and a hole was created here. This electron moved to this place and a hole was created here. You can see what is happening. Electrons are moving this way and holes are moving this way. Holes are moving just like positive particles and electrons are moving in the opposite direction. So, electrons moving this way, holes moving this way, and both motion of holes as well as electrons causes the electric current to flow in a conductor, in a solid. Now, let me go back to that story. So, when other electrons move into these holes, the holes shift to the location held by these electrons earlier. So, the holes move in the direction opposite to that of electrons. They move like positive charges. Both electrons and holes contribute to the flow of current when an external potential difference is applied across a piece of pure silicon. And this pure silicon is therefore called an intrinsic semiconductor. In the next lecture, we shall see what happens if a small impurity is added to an intrinsic semiconductor. These semiconductors are called extrinsic semiconductors, and we shall also see what happens if a particular element is added, say and causes conductivity in a different way. So, we shall distinguish between p type and n type semiconductors, and we shall ultimately see the property of a p-n junction, and we shall see how rectifiers work.